Hi everyone, welcome back. In this last video in our unit on electric potential and capacitance, we're going to talk about how energy is stored in a capacitor, as well as the concept of dielectrics. So first of all, here's our equation for the energy which is stored in a capacitor. It's 1/2 CV squared, which is 1/2 Q squared over C. And we'll come back to where this comes from. We're just presenting it for now. And what happens is that capacitors store electrical energy by creating an electric field between their plates, and it's actually a type of potential energy. And that's why the voltage or electric potential is involved here. And remember that this voltage is equal to Q over C, because C is Q over delta V. So C in these equations is the capacitance, delta V is the potential difference, U is the electric potential energy, and Q is the charge on the plates. So where does this come from? If you think about potential difference and charge, if we plot this, then we could multiply these two variables together, and when we do the area of potential difference versus charge, well, remember that that is joules, because voltage is defined as joules per coulomb, charge is coulombs, so the area is joules, or energy. And then if we split this up into small pieces and think about the area of a triangle, the area of this is going to be 1/2 QV, or 1/2 VQ in this case. And remember that C is Q over V, so that means that Q is equal to CV or VC. So that's where 1/2 CV squared comes from. And this is what you see most often, is 1/2 CV squared. And the other way to do it is to replace V with Q over C, so you get Q squared over C times 1/2. So, but this one here, the 1/2 CV squared, that's what you see the most often. And it's also worth pointing out that the slope of this line, which is basically delta V over Q, that's 1 over C. So that's important to see. Now, we can look at this from a calculus perspective and recognize that voltage, or potential, is work per unit charge, or energy per unit charge. And that's also dW dQ, a little bit of energy for a little bit of charge. Then we recognize that V is equal to Q over C. And if we rearrange this, we have dW is equal to V dQ. So we plug in that V is Q over C here, and we get dW is Q dQ over C. And then we just integrate, because our variable is Q, we integrate from 0 to Q, pull the 1 over C out, and that's where we're going to get our 1/2 Q squared over C. And then we can plug in Q is equal to CV to get our more familiar form. So that's kind of the calculus derivation, which is another way of finding the area on that V versus Q graph. So for example, a 3 millifarad capacitor, so C is 3.00 times 10 to the minus 3 farads, which is pretty big actually, is connected to a 12-volt battery. How much energy is stored in this capacitor? Well, we just have to use our equation that the electrical energy stored is 1/2 CV squared. So that's going to be 1/2 3 times 10 to the negative third times 12 squared, and that's about 0.216 joules. Okay, so that's how we calculate energy in a capacitor. Okay, now the next topic is the concept of a dielectric. So first of all, a dielectric is a filling that you put between the plates of a capacitor. And what it does is it increases the capacitance, or the ability to separate charge. Now, the way that this works is that there's a constant kappa, which is what we call the dielectric constant. And so if C naught is the capacitance without the dielectric, then C is the capacitance with the dielectric. And typically we say that air or a vacuum has about a kappa of 1. So what is a dielectric actually? It's a polar non-conductor that works by decreasing the field strength between plates. So these non-conducting molecules orient themselves so that their dipoles subtract from the field produced by the charged plates. And since the field is going to be reduced, the voltage is reduced. So how does this work? Imagine that you have two plates, and you have a positive plate right here, and you have a negative plate right here. Okay? So just by itself, this sets up an initial electric field, which goes like this. We could call that E naught. And that's coming from the plates. Okay? So maybe there's a wire attached at the top and the bottom, and there's a battery somewhere that's providing voltage to separate those charges. But inside, we put our dielectric, and the dielectric acts as a polar non-conductor. So it's going to separate by induction slightly. So if I draw a couple of molecules, I don't have to draw all of them, but I can draw some of the molecules in the dielectric. And what's going to happen is that they are going to polarize such that they have negative at their top and positive at their bottom. And why is that? Well, the negatives are drawn to the positive end of the original electric field set up by the plates. And you get the idea. I don't have to draw all of these. And what that does is that sets up E prime, which is an electric field which is induced by the dielectric. So it's the induced field of the dielectric. Well, what's the result of this? The total field, E, that we end up with is going to be basically the vector sum of those, but since they point in opposite directions, it's going to be E naught minus E prime. And what this does is this decreases E. So the electric field of the capacitor overall is decreasing. Well, what does that do? That's going to decrease the electric potential because we have the integral of E dr. And if E is lower, then the integral of that will also be lower. And finally, our definition of capacitance is Q over V. And if V is lower, okay, so as V goes down, C goes up. And so that is what a dielectric serves to do in a capacitor. All right, so let's just wrap up with one quick example problem. We want to find the capacitance of a parallel plate capacitor that uses bakelite as a dielectric. Now this, I looked up, and has a kappa that ranges from about 4.5 to 5.5. So we'll just say that it's 5 for the purpose of this problem. And if each plate has an area of 5 centimeters squared, and the plate separation is 2 millimeters, what is the capacitance? Well, C is equal to kappa times C naught. But C naught for a parallel plate capacitor is epsilon naught A over D. So then we just plug in everything, and from kappa we're going to have a 5. Epsilon naught is 8.85 times 10 to the minus 12th. I'm leaving units out because I'm a bad person, but that's okay. The area gets converted into meters, and that's 5 times 10 to the negative 4th meters squared. because, there's 100 centimeters per 1 meter, and we have to do that conversion twice. Then we just divide that by the distance between them, which is 2 times 10 to the minus third meters, and we get a capacitance, which is about 1.1 times 10 to the negative 11th farads, which we can move over the decimal point 1 and call it 11 picofarads. Remember, that's times 10 to the negative 12. Okay? All right, so that wraps up our unit on electric potential energy, and capacitance. And in the next unit, we're going to start looking at circuits and how these different concepts of electric fields and energy and capacitors, how they all combine to actually do something useful for us. So we'll see you next time.